can't think as people do. The machine is different.
What marvelous being! How gratifying! How gratifying!
So tonight I have the privilege of doing an introduction to the showing of Another Earth, and I've prepared a few slides to go through this. Another Earth is a very interesting, fascinating movie. It had 7 film awards and 13 nominations. It won the Alfred P. Sloan Feature Film Prize Award at the 2011 Sundance Film Festival. It's one of the top independent films of the year at the 2011 National Board of Review. It's a story of the discovery of a duplicate Earth and its impact on an ambitious young student and an accomplished composer. So what I want to do is go through a few topics. Basically, the question that we all are fascinated about is, are we alone in the universe? For centuries, Earthlings, including ourselves, have wondered about extraterrestrial life. And these wonderings and thoughts have included scientific thought and speculation, scientific experiment and observation, and of course fantasy. So what I'm going to talk to you about tonight are basically in these 3 areas: the search for extraterrestrial life, the search for planets in hospitable environments where life may exist, and then I'll conclude with some theoretical physics concepts on various aspects that are related to this, including the idea of parallel universes. So let me begin by talking a little bit about early speculations. We go back 2,000 years, and already Lucretius was quoted here in his writing on the nature of things: there must be other Earths inhabited by different tribes of men and breeds of beasts. So this was already a concept that people were beginning to think about. But of course, as people moved on and the general thinking advanced, there was also an overwhelming concept that the Earth was the center of the universe. And it was only with Copernicus that a real basis for formulating the model of the universe with the sun rather than the Earth at the center. We're still talking about a very small universe at that point in time. One of the characters in action at that time is this guy named Bruno, who actually wrote quite a bit about distant suns with exoplanets that might harbor life, much along the lines of what planetary scientists are doing today. This wasn't very well received by the establishment at the time, and I believe he met his early demise as a result of these concepts. Now, so those are a few highlights of distant past. Around the turn to the 20th century, in the 1890 to 1910 period, there were some interesting things related to this that happened. There was this Italian astronomer who observed patterns on the surface of Mars, which he called canali, for channels. And this eventually got misinterpreted by others as implying artificial structures, and he didn't mean that at all. He just meant that there's structures that are natural on the planet. But when people read this, they then immediately started thinking about the possibility that there was life on Mars. And all of this took off in terms of, we ought to talk about Martians. H.G. Wells wrote a lot about this in his science fiction working, and one of those was The War of the Worlds, in which these Martian aliens invaded the Earth. Tesla is a famous figure in science, and one of the things that's related to this that he was involved in was receiving intelligently controlled signals, he believed, that he thought might be coming from another world. And in fact, the press picked up on this, and there was quite a bit of publicity on this. But of course, you know, this was not at all the fact. He was not, in fact, receiving anything like that. Finally, I just want to mention Percival Lowell, who also studied Mars extensively and sort of advanced on this notion of canals, and in fact had all kinds of maps of these canals and was fascinated by what these Martians were up to and what great constructions they had made. Well, of course, we know this was all fantasy, and finally in 1965 the Mariner 4 was able to get close enough up photos of Mars to show, in fact, without any doubt, there are no higher life forms on Mars. It's kind of like this cartoon here from the New Yorker in which these two fish are concentrated in this little region of space called a fishbowl. And one of them says to the other, "I'll tell you something else I think. I think there are other bowls somewhere out there with intelligent life just like ours." So we're fascinated by the possibility that there is life on other planets. Mars has been a target for a long time. We know for a fact there are no higher life forms on Mars today. But then the question is, could there be lesser forms either today or in the past? This asteroid called ALH 84001 was found at the South Pole a few years back. It turns out that asteroids can be knocked off of Mars. This came from Mars. It's believed to be 4 billion years old, the rock. When something impacts the surface of Mars, it can give it enough velocity that the thing can escape the surface of Mars, float around the solar system, and a few of these things eventually land on Earth. Now, the South Pole is a great place to go looking for these rocks because if a rock falls out of the sky, you've got this huge white field, and something that recently fell out of the sky will be very visible. And so astronomers go around, planetary people go around the South Pole looking for these rocks. They found this one. Now, this one had some particular interesting features. In particular, there were organic molecules contained within this rock that could be associated with life. There were minerals that are characteristic of biological activity, and there were tiny tubular and egg-shaped structures embedded in this rock. Take note of the fact it's a very, very old rock. So the question is, do these have anything to do with life or do they not? Could these be fossils, for example? There's been a great debate on this for many years, and I have to say, I believe that it's actually inconclusive. There are those who think that this is some evidence that at one time there was some kind of primitive life on Mars, and a lot of other people feel that no, these can be explained in terms of just lifeless constructions. But we don't know. I mean, it is possible that life began on Mars in some mechanism like this, and then spread to the Earth from Mars. It's still a possibility. Now, Mars is only one site of interest in the solar system. There are many others. For example, the largest moon of Jupiter, where we know there's liquid water below an icy surface. The largest moon of Saturn, which has a significant atmosphere. Other moons of these large planets. And we continue to look for evidence of the life in the solar system. So far, we don't have any real direct evidence of this. But tonight, our interest is really not so much at this question of primitive life that we might find in some environment like this, but rather higher life forms, something like human life. That's what the movie is about. Is Earth the only home of higher life forms? Here we are at this one little location in our galaxy, a small galaxy in a very large universe with lots and lots of other galaxies and a countless number of stars. And I personally think it's very unlikely that there are not other environments out there where various types of life forms exist. So one of the strategies we can do to try to find this is to do radio communication. There are two strategies that have been employed. One is to receive radio transmissions from intelligent beings out in space. And the other is to actually make transmissions to them and signal them that we're here. These are called SETI and SETI. The other aspect of this search that I want to talk about is to actually observe planets, Earth-like planets. We want to find planets that are in a zone of a sun-like star where the environment is hospitable to life, namely the temperatures are right so that we have liquid water and things like this. We want a rocky object like the Earth. That's where we know life can exist. And people have looked at for these with telescopes on Earth. We also have the Kepler satellite, which is in orbit and has generated a large amount of data. So let me first talk about search for extraterrestrial intelligence. And this adventure follows the assumption that if there's advanced civilizations out there, and why wouldn't these civilizations be at least as advanced as us and maybe more so? Humans have only been on Earth for a few million years, whereas the universe has been around for 13.8 billion, so there's plenty of time for life forms to advance way beyond where we are. And given the laws of physics, one would assume it would be very natural for them to develop radio communication. And then the question is, what scientists say is, well, suppose they try to communicate through space, what frequency would they choose to communicate to people who maybe aren't expecting them to be communicating with them? And it turns out that the popular choice among scientists is a wavelength of 21 centimeters. It's a radio frequency of 1420 megahertz. And the reason for this is this wavelength can be produced by a spin-flip line of hydrogen. So the hydrogen, of course, is the simplest atom. And so a very simple transition within hydrogen produces this radio frequency. So it's a very fundamental frequency of the universe. And it's the one that a lot of effort has gone into thinking about, can we find signals from extraterrestrials communicating at this frequency and wavelength? Well, the search here began in around 1960. It was pioneered by this guy named Frank Drake. And one of the things he did was to try to identify stars that one might expect have a good chance of there being life forms. And so he focused his receiver on first this one, Tau Ceti, which is a G-type star. The sun is a G-type star. And so the assumption there was, well, this is much like the sun, so maybe this is a good place to look. It's only 11 light years away, so the radio waves would have taken 11 years to get here. And, well, there was no signal. So that didn't discourage him because, you don't find it on the first try. And so then he went to this other object, which is a K-type star. It's very similar to the sun, not exactly the same. When he turned his telescope on this guy, there was a big booming signal coming through, and everybody in the control room got very, very excited. And then the airplane passed overhead, and things quieted down, and there wasn't anything else going on. Well, they continued to then look for more and more searches, and over the course of the last several decades, people have gotten more and more sophisticated, done a lot of computer automated searches, looking for millions of different sources, and so far, nothing has shown up. But that doesn't mean we stop. But then we could say, well, okay, we're looking for their signals. Why don't we send them our signals? And so maybe we need to signal directly, and the question is, should we? Should we send them a signal? One view is, no, absolutely not. They're going to be much more advanced if they pick this up. It's unlikely they're not going to be more advanced. They would view us as primitive life forms. They would want to choose to exploit us, enslave us. They may even be hungry enough to eat us. So that's one point of view. On the other hand, there is the point of view that says, well, let's think about maybe they know a lot more than we do. Maybe they could help solve the problems of the world. Populations explosions, energy shortage, world of wars, many, many different problems. And the fact is, they would likely be so far away, distance-wise, that there'd be no worry about their coming here. The communication would travel at the speed of light, but the assumption is that transportation between this site and us could never be close to the speed of light. So even if they identified we were here, it would be a long, long time before they would ever be able to come here and taste our skin or whatever they wanted to have at us. So in 1974, actually, some astronomers took this radio telescope in Puerto Rico, Arecibo, and they actually sent out a message out to a globular cluster called M13. Globular clusters are collections of lots of stars. They're sort of an island of stars circling around the Milky Way galaxy. And the idea here was that since all of those stars are concentrated in a small region, you can beam a message in that direction and have a chance of, if some of those stars, or even one of many, has life forms, you might have a chance for them to pick up the signal. The distance is around 24,000 light years. So this signal that left in 1974 will only reach M13 in 24,000 years. And okay, we're going to have to wait a long time to find out if there's any message coming back. There's an image here shown on the left of this slide, which is kind of a reconstruction of the message that was sent. And there's a lot of technical details as to how you would take the radio signal and transform it into this, but I'll leave that for your future investigation. Prime numbers are involved, and there's an image of a person there, and there's a DNA helix, and there's an image of the radio telescope, and our location in the universe and things, or in the galaxy and things like that. Okay, so now let me turn to the search for planets. So far we haven't found any communication has worked. Maybe the strategy of actually finding planets is going to lead farther along the path. The first exoplanets, planets of stars outside of our own solar system, were discovered in 1995. And the properties we're looking for, as I said earlier, is some Earth-like planet, a sun-like star, and a habitable zone. That is, sometimes we refer to it as the Goldilocks zone. Not too hot, not too cold. So we have a sun-like star, which gives us a certain amount of radiation in that system. And then the planet has to be not too close to the star, because then it would be too hot. And not too far away from the star, because it would be too cold. We can think of the planets in our own solar system and how that works. The Earth is basically an ideal location in the solar system. The Kepler satellite has really advanced this field enormously. It was launched in 2009 by NASA, and what it does is to detect starlight's dip with each eclipse of the orbit of a planet around a star. So here you see a star that's shown in yellow there, and you see the orbit of a planet going around, and the relative brightness is dipping down by a small fraction of 1% as the planet eclipses the star. This is not a very large amount, and it's very difficult to measure, but Kepler manages to do that. And again, the goal is to find terrestrial-like planets, 1.5 to twice the size of the Earth, preferably in the habitable zone of a star, where liquid water and possibly life might exist. Here's a little video that shows how this works that I'll play. It kind of illustrates this. So the planet is going around the star, and as it passes in between us and the star, it eclipses the star and reduces the amount of light that we receive from the star by a small amount. And so the measurement you see here is the brightness as a function of time, seeing that dip. And for most of these planets, this dip can be quite small. This is a very sophisticated system. Well, here's a depiction of the planets that have so far been recorded. And you see on the vertical axis is the size relative to the Earth. Starting one there represents a planet that's about the size of the Earth. 10 is 10 times the radius of the Earth. Over on the right-hand side there you see Jupiter, Neptune, and the Earth to indicate these sizes. And then along the vertical axis is the orbital period of the planet in days. And that's basically an indication of how close that planet is to the star. We're looking for something that would have an orbital period of roughly 365 days. And so you can see that we're not, of the many, many planets that we're finding, there's tons and tons of planets out there, but they're really distributed in a very random way, and only a small fraction of them are actually going to be in the environments that we would anticipate has the possibility for life to form. Here's the census of what they've achieved so far. There's about close to 5,000 candidates, So that's where the Kepler satellite sensed that there was a dip. But remember, the dips are so small that one can't be 100% certain until you really investigate thoroughly. Only 1,000 of those have been confirmed as being for sure planets. And of that 1,000, 12 are small enough to be Earth-like and to reside in the habitable zone. And here's an artist's conception of these planets, starting from the Earth on the right to some of the others over to Kepler 22b to give you some feel for the various sizes of these. But all of these are thought to be rocky and temperature-wise to have liquid water, and therefore the chances that life could emerge there is finite. Okay, so that's kind of a little introduction. Let's turn now a little more directly to the topic of the movie. And the movie basically speculates on the possibility that an extraterrestrial life somewhere can be identical or nearly identical to the higher life on Earth. And in this movie, we're going to say we have a planet of the same size, geology, age, same species exist, has had the same evolution, the same individuals exist, the same organizations exist, America, NASA, the same leaders, the same president, the same Congress, the same NASA employees, the same professors. All of these things in the movie, as you'll see early in the movie, are imagined to be very similar. Let's talk a little bit about some of the theoretical physics that this suggests might be relevant. I have to talk about quantum mechanics. Quantum mechanics was developed in the 1920s. It's been a very successful description of the atomic and subatomic world. And in quantum mechanics, everything can be described by multiple states. When measured, they appear randomly in one of those states. So the basic point is that each step on an evolutionary path involves matter in a fundamentally random and unpredictable process, step by step, random, unpredictable process. Everything is the end result of a very long set of random steps. Now, Einstein never was satisfied with the randomness of quantum mechanics. He was a great scientist, and he delivered a lot of great innovative theoretical physics to us that's been confirmed beyond anyone's expectation. But the one thing that he had a lot of trouble with was the development of quantum mechanics. He said God does not play dice. He was convinced if one really understood what was going on in the fundamental level, the atomic and subatomic level, we should be able to predict the outcome of events. They shouldn't be random. But today, we physicists completely accept the notion that at the atomic level, all outcomes are random, and any one of the possible outcomes can happen without the ability to predict. If you put together lots and lots of atoms, like a person, then the statistics adds up to make things more predictable, because we have an awful lot of atoms. But at the individual atom level, it's very random. Well, Einstein didn't like this. And in the 50s, a physicist named Hugh Everett came along and proposed a different approach to this. He accepted the fact that the outcome could be random, but what he said was, of the multiple outcomes, nature will actually split into multiple worlds, one for each possible outcome. So this suggests the existence of parallel universes. In other words, every time, for example, just as an example, every time a coin is flipped, okay, another universe is created with exactly the same history. The past is the same up to that point when you flip the coin. But in the other universe, the coin comes out with the opposite result, and history diverges. So we have another universe, a parallel universe, where the history has been the same, and now we move forward in these two different universes. And his notion of this many worlds interpretation of quantum mechanics was that as time goes forward, you produce many, many, many universes, and they're all diverging. Now, another possibility that leads to this notion of multiple universes is through inflation, which is the notion of what happened during the Big Bang, and the multiverse. The multiverse is a theoretical reality that includes the possibility of infinite number of parallel universes. And the idea there is inflation creates a bubble during the Big Bang, which leads to the universe we know, but it also leads to an infinite number of bubbles that have different properties and create different universes. And over all the bubbles in the multiverse, everything that can physically happen does happen an infinite number of times, because there's an infinite number of these bubbles. Well, this is actually there's a lot of literature on this. A lot of people have been speculating, reputable scientists with tenure. The question is this testable? And some of the more prominent physicists think this is hogwash. For example, Paul Steinhardt, who's a very reputable particle theorist, calls this scientifically meaningless. You can look up this Nature article. Nevertheless, this is speculation about the reality of our existence. One of the concepts that I'm sort of fascinated by is the possibility that we live in an infinite universe. In fact, the universe may be infinite. The measurements of the shape of the universe to its observable edge are consistent with this possibility. We can only look out so far. We can only look out to the distance that light has been able to travel in the 13.8 billion years that the universe has been around since the Big Bang. But the question is, what is beyond that? And we can make measurements that indicate that the universe continues to go beyond where we can see. Now, there are a limited number of ways atoms can be arranged, and the patterns may repeat. And if they do, there will be another Earth out there. Technically speaking, the possibility of realizing the story told in another Earth is so small, while scientifically possible, it is highly unlikely. But it is a fascinating story. So let's suspend disbelief and enjoy. And the question you're going to be left with as you watch this movie is, what if you're not unique? What would you do if you met another you from another Earth that looms like a mirror in the clear night sky? What would you say to yourself? So I hope you enjoy this movie as much as I did. Thank you very much.
I don't know enough physics to understand why you're less random because there are more atoms in you than a single atom.
So if you flip a million heads, so if you flip one coin, I'm sorry, there's a 50-50 chance that it'll come up heads. But if you flip a million coins, then the probability is, with a narrower margin, that half of those will come up heads and half will come up tails. In other words, they're not going to be 50-50, but they're going to be, they're going to come out to be closer to 50-50 than just 1 or 0. I don't know if this makes sense.
Because of the average?
Because of the average, as you build up statistics, the average accumulates. And you're just going to have more heads than tails or more tails than heads. But the ratio, if you make the ratio, it's going to get closer and closer to half. Whereas when you just do one coin, the ratio is either 0/1 or 1/0. And as you flip a million of these, the ratio is going to come closer and closer to a half. And you trillion, it's going to come. So when we're talking about a very large number of atoms, if each atom is completely random, the outcome of many of these can be more deterministic. And so when you see a dog run out in front of a car, it doesn't hesitate, it gets out of the way of the car. It's not a random event. Yeah. Does that make sense?
It does, as long as you only have two choices, as long as it's only binary.
Well, as soon as you have multiple choices, the ratio, you'll have more ratios, but if you have 4 choices, then it can only be, if you only do it once, you only have one. Like if you roll dice. Roll one dice, you're only going to get 1, 2, 3, 4, 5, or 6, right? And if you do it a million times, you're going to get roughly 1/6 the time, roughly, is going to be one of each of those outcomes.
Can you explain a spin, ellipse, line?
Okay, let me explain the spin flip. It turns out that the electron and the proton in the hydrogen atom is just a proton and an electron, and each of those is actually spinning. All fundamental particles that make up atoms have a little bit of a spin to them, it turns out. We've measured that. And the spins can either be in the same direction, so the proton and the electron are spinning in the same direction, or they can be spinning in opposite directions. Those are the two possibilities. Quantum mechanics tells us that everything is quantized. You have possibilities that are limited. And so it turns out that there's those two possibilities. If you look at the proton, you'll see that it's either spinning in one direction with the electron, or they're spinning opposite. Now, it turns out the energy levels of those two configurations are slightly different. One of those configurations has slightly more energy than the other configuration. So when a transition occurs, when the flip occurs, the energy of the atom goes from a higher energy to a lower energy. And what does it do? Well, it emits energy. And how does it emit energy? It releases a photon. And what's the wavelength of that photon? 21 centimeters. So this is a very magic wavelength of light that comes from the most fundamental atom when you have this orientation changing and the energy of the atom changing. Does that make sense?
Yeah, thanks.
Thank you. Thanks for your presentation. The question I wanted to ask is about the multiverse here towards the end, where you flip the quarter and bifurcate to two universes instead of one. So in that simple example, where you're just going from 1 to 2, before the quarter is flipped, is the idea that there is only one, and it becomes 2 instantaneously, with the second one acquiring all the history of the original? Or is the idea that the 2 have existed simultaneously in sync until the quarter is flipped and then they separate?
Okay. So the idea is that today there's an infinite number of universes that are the consequence of all the random events that have happened since the time of the Big Bang. And every time we go through one of these events, and they're happening continuously, the existence is splitting all the time. So before the coin is flipped, we are aware of the universe we are in, but from the past history, from sequences of different events, there's a plethora of such universes that in existence. This is the idea that Hugh Everett put forward. It's a counter-argument to try to overcome the objection to the fact that we just cannot predict the outcome of a random event. One of the examples I like to think about is a radioactive nucleus. We know radioactive nuclei decay with a certain lifetime. And so we know randomly they're going to decay at some time over a period of time. Say the lifetime is a year. Then it'll decay away a year and there'll be less and less appearing. But on any individual nucleus, we don't know when it's going to decay. Everyone is random. They're all completely random. And you can't predict this one's going to go first, that one's going to go second. That's difficult for people to accept. And physicists are just people. And Einstein was just a human being. So he had a hard time thinking that we couldn't eventually figure out a way to actually determine which nucleus would decay first and which would, there's some kind of probabilistic thing in there. But the fundamental theory of quantum mechanics is no, it's absolutely random. And the many worlds theory then was a kind of a counterproposal, which is not very broadly accepted, but it's kind of coming into interesting considerations in terms of this old idea of the multiverse. Does that help?
When did you become interested in physics and astronomy?
I became interested in physics and astronomy far too long ago to recall, but it was at least 60 years ago. Okay, you can shut it out and I'll repeat it.
Okay. I know that we have a new telescope being launched in the next couple of years, the James Webb. How much greater will our capacity be to find other planets as a result of that being launched?
Okay, so the question has to do with the James Webb telescope and its relevance to finding planets. I'm not an expert on that topic, but I believe that it's not going to advance our ability to find planets very well, because that's a very specialized area of investigation. It's really designed to look at the deepest places in the universe, which are not a good place to find planets because they're really too far away to see. In other words, in order to detect either the eclipse, or there are a few other methods for detecting these planets, we really generally have to concentrate on stars that are closer to us. And the goal of the James Webb is really to look back in time and find what was going on at the most distant parts of the universe, which means much earlier in the history of the universe. Yes?
Sorry, we have a question with the microphone. Hang on, guys.
Sorry. So off of this picture, the other Earth looks really close to this girl's vantage point. Wouldn't she be concerned about the gravitational pull?
Where are you? I'm sorry. Where? Okay. So absolutely, and that's why we said suspend disbelief and enjoy. Absolutely. I mean, this is fiction in this truest sense. But if you just allow some of these physical concepts to slightly fall out of the picture, I think you'll find it a fascinating movie.
I got a little confused with the Kepler search for likely candidates for planets like the Earth.
Yes.
When I saw the graphs that were based on a function of time, or time of orbit, which is our time and our orbit, how is that translated to stars billions of years away, light years?
So these stars are not too far away from us. The point here is that when the dip occurs, as the planet passes around the star, we see a dip in the light intensity, and we can measure how often that happens. So if it happens every 100 days, then we know that planet is orbiting the star with a period of 100 days. If we were looking at the Earth from some distant, looking at the sun and the Earth, we'd see this dip occurring every 365 and a quarter days, right? That's how long it takes for the Earth to go around, and we'd see this dip. And so by looking at how many days it takes for the dip to occur, we're making a measurement of how long it takes for the planet to go around its star. And if it goes around more quickly, then that implies that the planet is closer to the star and probably not in the habitable zone. We want it to be out here near the region of a year so that we know the planet is out there in a more hospitable situation, like liquid water possibilities. That's what the time here represents. Does that make sense? Or
Yes, except a day on Earth could be very different from
okay, so we're not worried about a day on Earth. A day on this planet. We're worried about a year on the planet. The planet certainly may be spinning at a different rate. That's what defines a day. So a day could be 100 hours. It could be 10 hours. We can't tell what that day is. But the important thing is the distance from the star, because that more or less defines the temperature of the planet. And that's the only thing we're really talking about here. We're not talking about a day on that planet. Okay?
Any other questions? No? Oh, one more.
Wait for the microphone so we can get your voice.
Do we have any idea how circular those orbits are, or if like close to the star but highly elliptical?
There is data that gives some information on the nature of these orbits from the analysis of this data. And if you're really interested, I recommend you go to the NASA Kepler webpage. And there's a huge catalog there of these thousands of candidates in the stars. And there are star systems with several planets that have been found in these systems. And they give you some evidence of what that looks like.
Okay, thank you, Dr. Brau.
Okay, thank you all very much.